Hello everyone, my name is Shweta and today I will be discussing our work, HyCache, hybrid caching for accelerating DNN input preprocessing pipelines. Deep neural networks today have become ubiquitous. They have enabled breakthroughs in computer vision by enabling image recognition, object detection, and image segmentation at pixel level. Not only that, they have also empowered speech applications like text-to-speech generation and enable real-time language translation. While DNN models continue to advance, their training pipelines consume an ever-growing amount of data. These pipelines demand significant time and resources. But even before the training can begin, the input data must go through something which we refer to as the preprocessing pipeline, in which the data is first fetched from the file system. It is then decoded and must go through several augmentation steps. This could include steps like cropping, flipping, normalizing for image pipelines. Finally, a batch of these tensors is created and is transferred to the GPU for training. We keep on repeating this process for each data item that is in the dataset. While DNN trainings mostly happen on the GPU, the input preprocessing pipeline typically occurs on the CPU. Given its relevance to training, this pipeline has been significantly studied by both industry and academia. A report from Google shows that approximately 92% of their DNN training jobs are stalled by preprocessing pipelines for over 50 microseconds. Over 62% of the jobs wait a millisecond waiting for data, and approximately 16% of their jobs stall by over 100 milliseconds waiting for the input preprocessed data. Similarly, at Meta's data centers, today preprocessing consumes more power and energy compared to the GPU training itself. We also analyzed around 6 DNN pipelines to quantify how much preprocessing stalls can impact end-to-end DNN training latencies. And across these 6 models that cover image recognition and object detection, we observed that the training can stall by approximately 2.3x due to the input pipeline itself. Over here in the graph, the black bars show an emulated scenario where there are no preprocessing stalls, and this is compared to the end-to-end DNN pipeline times. Let's briefly go back to our pipelines, and in this talk we would be focusing primarily on the preprocessing, on the input preprocessing itself. And one obvious way to address these preprocessing stalls is to cache the intermediate results that we obtain across different steps. And this can primarily avoid any redundant work that might be required in future epochs. And it could significantly reduce fetch and compute times. While, for instance, over here, say suppose if we cache the output from the crop step, then we can avoid across future epochs fetching, decoding tensors, and even cropping them, and could just focus on flipping, normalizing them, and then continuing with the DNN training as usual. And because of all of these benefits of caching, again, this has been widely studied by many academic and some industrial works. In the next stage of the talk, we'll discuss what generally these prior works provide and where they lack. So many existing frameworks like TensorFlow support caching, but it is only in a very limited fashion. They allow caching the output of a pipeline step only if the entire output fits in the memory or storage. If not, then they cache nothing. And they miss the opportunity for reusing this data. Given that data sizes today are already really large, and how decoding can further inflate the size of the data, typically a policy where we try to cache all or nothing ends up caching nothing in memory or storage. We believe that any efficient caching framework should allow caching intermediate outputs partially, storing any fraction of intermediate tensors as needed. This would enable reuse for expensive steps even when fully caching them isn't feasible. While partial caching intermediate tensors seems intuitive, it is difficult to realize, as it demands that the preprocessing framework must be able to ingest tensors from different steps. Next, many prior works often cache either in memory or storage, but not in both. This can sometimes lead to duplication. For example, data which is cached only on storage may still be loaded into memory via OS page caches. Hence, we will see the same tensors in both memory and storage, wasting space in memory. We believe that any efficient caching framework should enforce exclusive placement of tensors in either memory or storage, but should not place the same tensors in both the tiers. This would avoid duplication and would maximize our caching capacity. While this seems again intuitive, to mutually cache exclusive tensors, our framework must have the ability to control and manage the tensors that get cached in different tiers of caching. Now, while it is important to store mutually exclusive tensors in different tiers, this alone is not sufficient for efficient resource utilization. Memory and storage differ not just in size, but also in their access latency. Caching the same step in both these tiers ignores their differences. Some steps may benefit more from being in memory, while others may be better fetched from the storage and then recomputed. To this end, we believe that caching decisions must be tier-aware. We must select the ideal step to cache in memory or storage based on their characteristics, which includes what is their size, how much time does it take to fetch from those tiers, and what is finally the recomputation latency of placing tensors in different tiers. However, designing such a framework is not very easy. To this end, we introduce HyCache, a hybrid caching framework that enables partial caching of intermediate outputs. It exclusively places cache data in memory or storage and does a coordinated tier-aware caching across both memory and storage. It also provides a simple automated library interface that minimizes any programmer effort. We shall now see some of the design ideas behind HyCache. First, HyCache is designed to reduce the burden on the programmer. It automates many of the low-level decisions required to efficiently manage memory. For instance, when given a memory budget, we cannot use all of it for caching. A portion of this memory must be set aside for the pipeline's internal operations, to which we refer over here as working memory. HyCache automatically estimates the size of the working memory and subtracts it from the overall memory budget to avoid any errors. To understand what might be the working memory, it takes into account the number of fetchers, which are parallel threads which simultaneously fetch data from the disk or storage, the prefetch depth, which determines how many of these data items can be buffered in memory, and the size of a batch, which again implies what would be the batch size for all these data items. From here, it's able to estimate the working memory size and subtracts it from the overall memory budget to determine the size of the memory cache. Next, we move on to analyzing or profiling what would be the benefit of caching each step in either memory or storage. HyCache profiles around 1% of the total training data set to obtain a graph like this, which shows for each pre-processing step, what is the expected size of this step when of the intermediate outputs after the step is completed, and how much time would be saved if the step is cached in memory or in disk. Given these two information, which is the memory cache size, even the disk budget, and along with that, the cost-benefit analysis of each step, HyCache uses an ILP solver to generate the ideal step to be cached in both memory and in storage. HyCache next generates a pipeline which uses these ideal caching steps to, it automatically creates a pipeline which uses these ideal caching steps and can be automatically fed to the DNN training pipeline. By using the profiler, which performs cost-benefit analysis for memory and storage, and an ILP solver, HyCache enables coordinated caching across different tiers. By automatically generating a pipeline which is able to ingest data from different steps and from different tiers, HyCache is able to enable partial caching. Finally, we provide an automated library which takes in three things as input: the dataset, disk and memory budget, and pipeline from the user. And it returns us with the following things. It reserves a portion of the memory as working memory. It populates the memory and disk cache. And finally, it returns a pipeline object which is able to ingest data from different levels. Being able to generate the populated memory cache and disk cache is generated in such a manner that the tensors stored in both are exclusive of each other. We evaluate HyCache on a server equipped with 24 vCPUs and 170 GB DRAM. We observed that across 6 diverse preprocessing pipelines spanning from voice, object detection, and segmentation, HyCache is able to offer up to 5.3 times speedup over the generic case where no caching is performed. HyCache also can very well adapt over different hardware configurations. We test HyCache over configurations varying from small hardwares like with 12 CPUs and 85 GBs of memory and just 128 GBs of disk size, to configurations with 1 terabyte of disk size and 48 vCPUs. We see that across different configuration, HyCache adapts very easily. For voice pipelines, even for configurations with very limited resources, HyCache is able to deliver a speedup of over 3x, whereas for configurations where it has sufficient memory and storage resources, it is able to deliver a speedup of over 7x. To summarize, HyCache enables partial, exclusive, and coordinated caching across both memory and storage, maximizing reuse even when fully over multiple prior works. It provides an automated library that requires no changes to the model or the training loop and makes it easy to integrate with existing DNN training pipelines. HyCache is adaptive and profiles the pipeline and memory constraints to optimize your caching plans, and it delivers a speedup of up to 5.3x over a no caching scenario. Thank you. I will be happy to take questions now.